All right, Sid and Alex, and we're doing binary expression trees. Oh, now we're good?
Sir, can you move your head, please?
My head?
David Park.
You're right in front of the camera.
There we go.
You got it, guys.
All right, so types of binary expression trees. We have algebraic and Boolean. What this means is like binary expression trees, think of them as like calculators. So algebraic would be more like addition and subtraction. Boolean is more like false and true. So these the variables and the numbers, constants. The operands basically like as you go up the binary tree, it's like adding numbers together and multiplying them. So we have functions like addition, subtraction, multiplication, and division. The components of it, the vertices are like how they connect. And the lower components are the children. So the children are connected to the top through vertices, and at the top we have operations that calculate the two together. So as it goes up, they like if we have like 2 and 3 and then a plus sign, that'll be 5. And then over here we might have like 4 and 6, so it's 10, and then those might like subtract into each other. And so overall it's like a mathematic equation as it goes to the top. So it can be easily used as a calculator. It's like a good function of that.
Wow. Great. That was so
Here's
good.
a picture of a whale. This whale is blue. It's very nice looking. It's right in the background.
Okay, bonus question. What type of whale is this?
Beluga.
No.
Whale
It's a
shark.
whale shark.
Whale shark.
Shark whale.
Whale shark.
I said
It's
that.
a whale shark.
Why does nobody listen to me when I say the right thing?
It is not a whale. It is not a mammal.
It's
It is
a whale
shark.
shark.
They grow to be about 35 to 40 feet long.
That's what makes it
And
Shark
they
bait.
can't
Ooh-ah.
bite you. They don't have teeth.
You know.
They have
That's
ballots.
no fun.
Yeah,
Bailey.
No, you need tits to have.
That's how they feed.
Okay, is there
To be
more
a
to this
mammal?
presentation?
I'm a mammal.
Okay, so
You
get
have
back up.
This is a
I know, but I meant like a female fish.
TV
Well, there are male
So currently, this is the largest fish on the planet.
Wow.
Nope. Deep sea. You got those ballots.
Should I keep on recording or
They're not as massive as that.
Somebody's gonna find a megalodon.
That would be amazing.
It's gonna happen.
That'd be so cool.
And less than 5 years after that, someone will have the Megalodon movie
That would be
terrorizing theaters.
So there's
Okay, back to the presentation.
algebraic example like x plus 5 divided by 3 and 3x plus 8. Like it's like a visual way that the computer goes through that the program goes through the operations in like this recursive vertices in the children. So like create a calculated like mathematical equation.
So here's a Boolean example, and that's another way we can express binary expression trees. So this is true or false. We use this type of V that's blue to represent or. The red upside down V is and this sort of squiggly line that's green is not. So it's true or false and not false. And that's just sort of a way we can represent Boolean examples, sort of if-else statements, true, false, logical statements. The algorithm to evaluate sort of math in the binary expression tree is sort of relies on recursion. So you first recursively evaluate the left subtree, then the right subtree and get that value. And you just keep on going, calling itself over and over until you get the final value starting from the bottom. Then you work yourself back up and using the nodes the operations to evaluate the two different sides of the node in order to get your resulting value. And it all relies on recursion. First off, there's the position interface, and that deals with the elements, getting the elements and sending the different elements to the different nodes and vertices. And then we have the tree interface. I don't know if you might have more on that, but it also relies on the position interface, and we use it it has like sort of just a list of different methods to get the different positions, the different sizes, print out the different lists and arrays that we do have with the tree. And over here, I'm not sure if you can see it clearly, but these are some methods that deal with the different positions within the tree. So this one is public position root, or returns the root of the tree. This one is public position parent, the parent of a given node. This is internal, so it represents whether a given node is internal, meaning that it's an operation instead of an operand. And this one is external, so whether it's an operand, an operand instead of an operation.
Yeah, and sort of in like an object class oriented way, once you have the interface for the whole binary tree, you can use another class and take the methods from that and use it to make a calculator using binary expression trees. So the whole thing just like simplifies it, but you can do lots of complex ideas within the interface once you have it all together.
This is the binary expression tree interface, so we're getting more specific to binary expression trees. It extends the tree to the subclass of that interface, and it also deals with the same position sort of idea and concept, getting position and setting positions, checking whether there's a left position or the right position, and returning the left and right positions within the subtree. Now we're getting more into the actual implementation with the Euler-Tor class. It's just the way, the Euler-Tor is just a way of traversing a binary expression tree. So where we first off start is creating a binary expression tree, an actual tree, and then using the different recursive methods, we evaluate the left part and we evaluate the right part. So over here it says if tree has left, and then you evaluate the left part, and you just keep on going as long as there is an operand and an operation until you finally get the resulting value. And you do the same thing with the right. And once you finally have the two values at the two opposing ends, you work your way back up and evaluate it at the very top operation to get the resulting value. And it all, like I said, relies on recursion. This is the binary expression class, which sort of just executes the previous class I just talked about. And it uses a visit right method to start at the very left and go right. And as you can see, it just sort of calls itself over and over again, return Euler-Tor tree.root, and it returns the value of the expression. And that's sort of, by using all these different interfaces that extend each other and are subclasses of each other, that's sort of how the binary expression tree class actually implements the different concepts that are involved and get the resulting value.
The recursion works because it calls something from the right, it calls something from the left, and it puts it together with the operative at the top so that it sort of, the calculator goes together through the interface.
And the last class I'm going to show you, it's kind of separate from the other classes that I showed you already, and just to print out the expression. And this one isn't as complex as the ones I just showed you. It just prints out a parentheses if the node is internal, then prints out the elements involved, so like 5 plus 3. And then it prints out the closed parentheses to close off that expression. And yeah, that's your presentation on binary expression trees.
Yeah. Yeah.